All right, Lina, did you get? I mailed you.
Yes, yes, I'll post
Yeah.
it.
Okay, great. All right. So today, this week we'll have Sam DeHority from Yale. He will give 3 lectures on Orientifold lines from CoHA modules. CoHA means cohomological whole algebras. Okay, Sam, please.
Great. Thank you so much. Actually, I guess first I should mention that my current affiliation is the Perimeter Institute, although I'm also sort of affiliated with Yale. But yeah, I want to really make sure that I appreciate the
Okay, walking along
position.
perimeter, but originally from Yale. Yeah.
Okay. Uh, right. So I wanted to discuss a couple of things. So um, most of what the lectures are going to be about is going to be about this paper 25 of myself with Losha Letintsev. Um, but then I also want to discuss some work in progress that should hopefully come out in the next couple of months with Alyosha and then also with Wenjin Liu um, that um, has to do with some of the same sorts of objects of line operators in HT theories and cohomological Hall algebra representations that is relevant for the discussion that we're going to have today. So what's the general class of problems that we're trying to solve? Is we want to understand um, categories of line operators in um, certain very nicely behaved quantum field theories, namely those that are holomorphic topological, so as close to topological as we can get given the circumstances. And in the nicest possible situation, we can hope that this category is described algebraically, namely that our category is the category of modules for some algebra with whatever type of additional structures the algebra requires in order for this statement to make sense. Um, so uh, the kind of canonical example where all of the intuition really should sort of come from is if we're in actually a 3D topological theory, theory which is sufficiently dualizable, then you expect the category of lines to be equal to um, the category of modules for a Hopf algebra. So H is going to be a Hopf algebra um, together with a um, a braiding structure. So this should be a triangular, or at least quasi-triangular Hopf algebra, because we have line operators and we also have a braiding between them. And because it's a topological theory, we can fuse lines together. So we always have an algebra structure coming from the local operators that can end on a line. But with additional topological structure, our algebra which we are categorifying, is has some additional structure. So
Should
I'm
I have in mind, sorry, uh, something because it's kind of for mathematicians, it doesn't make this left-hand side of the statement doesn't make too much sense, but for 3D topological, like for Chern-Simons, it's what category of finite dimensional representation of UQ of G of
Yeah,
okay.
exactly. Yeah. So we want our example is going to be UQ of G mod for a finite FD for and these are our Wilson lines. Um, Wilson lines in the Chern-Simons theory with this the gauge group corresponding to the finite dimensional algebra G. So we're gonna approach this general problem by studying a very specific, corner of this theory of studying Orientifold lines in the physical theory. So this is our physical setup, and what we're going to do is we're going to take expectations coming from the physical situation for what our structures or category is supposed to have, and then try to recover those structures in some mathematical context. So what is going to be the physical setup that we're going to use to try to, find some inspiration in this mathematical objects? Well, instead of 3D, we're going to study 4D theories. So one of our topological directions is going to become complex, but our lines are still topological lines. So our setup is we're going to have R2 with coordinates X and Y, and then we're also going to have a complex plane with coordinate Z. And then our lines are going to stretch along the Y direction. And they're going to be fixed at a particular point X, and also at a particular complex number Z. So starting from this theory, in order to define it on this like funny quotient of space-time, where we take a non-orientable Z mod 2Z quotient of that corresponding space, which is given by the following map. So we want to take X, send it to its negative, Z, send it to its negative. And we have to also do something to the field content of the theory. So plus some way of identifying the fields on the two sheets of this cover, plus an identification or an action on fields. Which, for example, if we're going to have a pure gauge theory, so in some sort of G gauge theory, we want a Z mod 2Z automorphism of the group should act on our group. And you expect to be able to then define the theory on this this background where we have the same topological direction on which our lines are switched, but the remaining part of space-time is this kind of cone over RP2. So if we take a sort of small linking sphere around this line, this gets quotiented to some RP2 quotient of that sphere. And these have been studied reasonably well in physics. And we can ask on this category of lines that lie at this orthofold, what basic sort of structures do we expect? In order to answer this question for Orientifold lines, the first thing we should try to do is understand what is supposed to happen for ordinary lines, because in particular, if we have some lines in the Orientifold theory that, lie far away from the singularity, then those are just going to have the structure of our ordinary line operators. So we'll try to first answer what sort of structure we expect the category of ordinary lines to have.
Sorry, I'm a bit confused. So you consider 4D theory, yeah, that's your point. You add it one. So then you consider category of lines and what in 4D theory, n equal 2 or what?
Yeah, in a 4D holomorphic topological theory, so if it's yeah, we're assuming that um we have a holomorphic topological factorization algebra. And in particular, a great way to get such a theory is to start with the 40n equals 2 theory and take its holomorphic topological twist. So this has enough symmetry to produce a theory such that the observables don't depend on their position in two directions and only depend holomorphically in one other direction. So this gives us a theory in two topological and one holomorphic directions. But there's other 4D holomorphic topological theories that don't necessarily come from this twisting procedure. So a concrete example to have in mind. So here's one example are these 40n equals 2 theories after their HD twist. Another example is going to be 4D Chern-Simons theory. So you can also just write down a classical action for a 4D theory and then notice that it's actually topological or holomorphic in the same way that Chern-Simons, you notice, is a topological theory. But probably the main example is exactly as you said you want to think of, is starting from a 40n equals 2 theory and taking this holomorphic topological twist. Great. So what do the line operators in a 40HT theory have? Well, first of all, it's a category because you expect if you have two lines, then there's a vector space of local operators that lie in between those two lines. And then there should be some additional structure coming from our ability to move our line operators together. So what sort of structure does this give on our category? Well, it should be a categorification of the same structure that we get on the factorization algebra of local operators in a 3D holomorphic topological theory. So a great way to get intuition, if you already sort of know how to do to study local operators to see what kind of category you expect for line operators in one higher dimension, is to see what happens for local operators in that lower dimension. So since we have topological lines that go in one topological direction, then the category should have a categorification of whatever algebra structure happens on local operators on R times C.
Can I model it in this example, which 3D Chern-Simons theory? So it's 2 plus 1, yeah, so I have what local operators on the Riemann surface, So it's what, Vezuminavitan or what? Or how should I?
So
Because too many words which does not kind of ring a bell.
right. So I don't want to think of Westumina Witten I want to think of as actually sort of a boundary. Instead, I just want to think of if there's a if you have 3D and uh this is a three-dimensional topological theory and you have lines, the type of structure you get on lines is the same as the type of structure that you get for just point operators in a two-dimensional topological theory.
Yeah,
And
but
so what's that
then
structure?
it's yeah, what is it? Yeah.
Well, it's the fancy word is an E2 algebra. But yeah, so
Hold on. But E2, it seems to be a pure topological thing, and if I remember
exactly.
correctly, but what about this Knyzhnik-Zamolodchikov, other things which do depend on the complex structure on the surface? Are they
Right.
ignored?
There's yeah,
It's
you
strange.
ignore it. So I'm not taking a boundary condition.
You do not take the boundary. Okay, all
I'm
right.
just trying to guess what the category of Wilson line operators, what structure it has, um, just based
All
on
right, all right. So it's
um,
because there are no boundary conditions for, I mean, for Chern-Simons, there is not too much topological choice for the boundary condition, if I remember correctly. Yeah, it should be holomorphic. Yeah, all right. So go ahead. Yeah.
yeah. So instead, what structure do I want to sort of generalize from the 3D story? Well, we have line operators, and then we have a monoidal structure, so we can fuse our two lines, um, which is analogous to the fact that we can kind of fuse local operators in a 2D topological theory. Um, and the uh, fusion is homotopy commutative. So it's homotopy commutative. Um, so when we fuse uh, two operators, say one blue and one green one, there's an S1, the like homology of S1 worth of ways of doing this. And as we integrate over that S1, we get a braiding or an isomorphism between the two ways of fusing our operators. Um, so if we have L and L prime, which is our monoidal structure, via the fundamental class of this S1, this is supposed to give us some isomorphism between the two different ways of taking the corresponding tensor product. And then you could ask about all of the coherence axioms that this satisfy, whether the monoidal structure is associative, only associative up to some choice of associator, and how this is compatible with the braiding. And yeah, there are many books written about this story. The in the topic at hand, we are trying to understand what happens when one of these topological directions becomes holomorphic. So we still expect to get a monoidal structure on this category. And the reason for this is that we can still fuse lines in the topological direction. So in the x direction, we have our two line operators, L and L prime. And as x goes to 0, since this is just a topological direction, we expect that we can actually take an honest tensor product of those two representations and get another object in that category. Now, the next thing that we expect is we expect to be able to translate our lines in the holomorphic direction. Um, uh, Technically, this isn't true for all 40 theories because this translation operation is related to the Hamiltonian in the theory. But in the all the theories that we're considering, there is, such a Hamiltonian or translation operator, and we can move our lines at one point in the complex plane to those at another point. And then we can ask about how can we fuse lines by moving them together in that complex direction. And this has been axiomatized in a number of different ways. I wrote down this story of a chiral category. So there's a paper by Sam Raskin, which abstractly defines the appropriate notion of the categorification of the notion of a factorization, a holomorphic factorization algebra, which is the structure you get of observables on just a holomorphic theory in 2 dimensions, or a global version of a vertex algebra. And we expect whatever this category is, that it satisfies this structure.
You don't need the additive structure. I mean, it's just symbolically z plus omega, yeah? It can be any curve, probably.
Yeah,
Yeah, I understand for physics reasons you take C, but just pure mathematically, you can define it for any complex curve, probably, instead of C. Am I right?
yeah, that's correct for like if your theory can be put on an arbitrary background.
Yeah.
The for the 40 Chern-Simons example, this turns out not to be true because the theory requires like a holomorphic 1 form. But yeah, most
Nowhere
theories.
vanishing holomorphic one form, or I mean, does it have to be calabi-Yau, like elliptic curve C or C star, or it can be any curve,
Um,
any
it
form?
may be possible on heterogeneous curves, but at least in uh, the action that Castellowit and Yamazaki wrote down, I think they do require it to be um, a Calabi-Yau surface or Poisson. So you want the 1 form to be yeah, non-vanishing.
Okay.
Because at where it vanishes, you have to impose some sort of some other sort of condition if you want the action to make sense. But no, I think it should be, yeah, it should absolutely be true for sort of arbitrary curves. But somehow I don't have a great handle on what happens outside of the case where it's, yeah, C star and elliptic curve.
Yeah, I'm asking because probably our matrix will appear very soon, and so its spectral parameters, they are typically restricted to one-dimensional Calabi-Yaus, so then to satisfy Young-Baxter.
Right, to get the Yang-Baxter. I mean, for us, we're yeah. Today, I'm only going to be talking about kind of the really local story, which is actually on the complex plane, and I'm going to ignore even the C star case. I'm going to ignore all kind of global issues. on that curve. Great. And so what do we want? So for us the category, it's going to be some other sort of monoidal structure, but it's going to depend holomorphically in an appropriate sense on a parameter in this complex plane. So in Raskin, there's a notion of a sheaf of categories, which is able to be defined algebraically. And in our case, these are actually all going to be like meromorphic maps in that variable. But we're going to avoid using the notion of chiral category. We're just going to take this expectation that we want a tensor product that depends on a particular variable, and then we'll have a very concrete model where you actually have, some rational functions and they depend on this extra variable. What properties do we want this to satisfy? Well, we want a version of the identities that hold for the fusion of operators in a like holomorphic field theory on C, which means we want a version of the vertex algebra axioms. And what do these give us? So we want to say that this tensor product is associative wherever both sides are defined. So the two sides of this map might have singularities, but wherever this composition is defined, we want to have an identification between these two tensor products. In principle, this is an extra piece of data of an associator, but for us, this is going to be a kind of obvious actual identity of vector spaces, and so we won't give a name to the associator that we have. The other thing that we expect is a meromorphic version of the braiding that exists in the topological case. So we expect to get an identification between the modules that we get when we've kind of fused them in a z-dependent way in one order, and that where we've fused them in a z-dependent way in the other.
What is tau z in your?
That's this translation functor that takes a line supported at some point and sends it to that other point.
Yeah, all right. And this meromorphic structure together with the braiding, does it fit in my axiomatics of meromorphic braided categories, which I forgot how many years ago I introduced it, or it's something different? Because I was motivated by, at the time, new concept of chiral algebra by Williamson and Greenfield. So, and so probably chiral categories just categorify chiral algebra, something. So is it the same or it's something new?
I think these two steps are exactly the same as your axioms. This Alyosha told me that they were the same, but I actually haven't done the detail of these corresponding checks myself. But
yeah.
My understanding is that with the braiding, these are exactly the same pieces of data.
Okay, but there will be more structures. Yeah, okay.
There's more structure coming from this extra topological direction. So the main additional piece of structure that we expect is some way of relating the actual monoidal structure to the chiral monoidal structure. And what do we want this to be? Well, we want an appropriate natural transformation from one monoidal functor to the other. And this is going to be a if both are given by vector spaces, we want a map of the corresponding vector spaces of the form where we take the tensor product with a z attached, and then this other construction where we translate one of the lines using the translation functor and then just apply the standard monoidal functor. So this compatibility morphism has to satisfy a particular commutative diagram that I'll write down when we talk about the corresponding diagram for Orientifold lines, because we'll see an extremely similar diagram, which will be, the exact same thing. So let's try to construct examples of categories that have these properties. And the canonical one comes from the structure satisfied by the category of finite dimensional modules for a certain Hopf algebra called the Yangian. So the theory, it's some theory that you can write down a Lagrangian for, and it's obviously holomorphic and topological. So if you make the relevant coordinate transformations, it only depends on topologically on two directions and holomorphically on one of those directions. And Costello and Yamazaki showed that if you really just using path integrals, write down operators that correspond to certain things you can insert into this Lagrangian and rigorously define the perturbative calculation of those operators, that they can construct a certain category which is isomorphic to the category of finite dimensional modules for a certain Hopf algebra called the Yangian of that semi-simple Lie algebra. So this is a Hopf algebra. It has an algebra structure and it has a coproduct. And it also turns out that the category of finite dimensional modules for the Yangian has all of the properties that we expect.
Sam, sorry. This category for finite dimensional representation, it's exactly meromorphic braided category, but you mentioned some extra structures. What are those extra structures in this example?
Yeah, so I'm about to explain sort of all of
okay.
that. I mean, the main thing, the extra structures that you get, you can see by taking the Gauss decomposition of the R matrix of the Yangian
interesting. Okay, go ahead.
So what's the data to define the Yangian? I'll go through this relatively quickly. So we have some collection of objects, which are these finite dimensional representations, which, there's this quantization parameter, so they're taking place over this kind of slightly funny grand ring. It's closed under tensor products. And then for all pairs of objects, we get meromorphic braiding up to swapping the two factors called the R matrix. This depends meromorphically on a parameter that we're going to understand that as expansion around infinity of that parameter.
What is W capital? Sorry. It's
Some
family.
indexing set.
No, I mean this W capital, it's what? Families of
Yeah, indexing
modules.
set for highest weight, families of modules.
Uh, yeah, but for Youngians, analogically highest weight is a polynomial. It's a Greenfield polynomial. So it's kind of not quite innocent. It's interesting.
No, that's true. It's yeah, it's not quite an innocent choice. So the
Why do you need this index at all? I
I
mean,
guess you don't. Yeah, that's
yeah.
yeah, I guess I want to say uh yeah, for all two representations, you know, V and V prime. Uh yeah, we can uh simply define the uh our matrix for these particular choices. Um and there exists such an operator that satisfies the Yang-Baxter equation, um, meaning that if you uh, compose, we'll write our braiding, which is sort of the R matrix flipped as a crossing of strands, that the left-hand side and the right-hand side of this diagram are equal. With the appropriate parameters inserted. So how we want to think of this as that let's see. So I guess this diagram is actually drawn top to bottom. So we want to think of the strands as lying at each of particular points. So one is going to be at 0 at Z and at Z plus W in the complex plane. And the these operators have to satisfy precisely this identity. And then how do we get this R minus structure? So this is written most clearly in at this kind of abstract categorical level, at least in this paper of Quattom, Toledano and Wendland, where once we choose a set of positive roots for the underlying semi-simple algebra to define a notion of upper and lower triangular for the weight spaces of these representations, then we can decompose our R matrix by taking its LDU decomposition. And the R matrix turns out to have the following feature that the lower triangular part of the LDU decomposition is closely related to the upper triangular part. So the upper triangular part of the R matrix is actually just the inverse of L at the negative of the corresponding parameter. And
okay. Well, I'm twicely confused. Actually, I have a question and I have a confusion, so I don't know what to start with. You have
okay.
okay, start with the confusion. R minus 1 on minus Z in the power minus 1, yeah. Is it what is written? That it's R minus Z first factor is just, and the last one is the inverse to something. And you consider what? Laurent series, these things as Laurent series in Z? Or what?
Yeah, so the constant term is actually the identity. So when we take this
All
expansion
right.
around
Yeah,
infinity,
yeah, that's what's my confusion.
yeah,
And
the
this,
leading order term is actually 1.
yeah, good. Yeah, but then comes my question. you see, you consider this R matrix as a collection of braidings between pairs of objects, but there is a universal quantum R matrix which lives in the completed square, tensor square of your algebra. All right, and then you can make it dependent on Z by twisting. I mean, it's all in Greenfield except of explicit formulas, which again I wrote so many years ago that I forgot. You can consider R of Z as an element of the tensor square of your quantum algebra, Yangian or UQ of G. Affine extended by the powers of Z. So then this factorization which you are writing is just, does it hold at the level of the universal level of algebras, or you have to do it at the level of representations only?
So in this paper by Gautam, Toledano, Laredo, and Wetland, there's one sort of slightly subtle point about like different asymptotic expansions based on how the size of Z compares to the size of H bar. For them, they're able to like write down this expansion universally. For the story with myself and Lyosha and Wenjin, we don't have such a nice description. So unfortunately, we are at the moment only able to say something about endomorphisms in an abstract category. So we define a category abstractly and get bratings for any elements in that category, which there's some technical issues to then if you want to get an algebra by doing Tanakian reconstruction, whether the resulting braiding actually gives you a meromorphic braiding on that category. I expect that something similar can be done, but unfortunately we haven't.
Yeah, it's technical thing, but okay, that's fine.
We haven't,
Category
quite
are
progressed.
fine. Yeah.
And so what does this give us? Well, it gives us the compatibility morphism or minus, and then also this braiding, which is given by the diagonal part of the R matrix. And so here we have our two tensor factors. The one standard tensor product, our standard monodal structure, comes from the coproduct that we were given, and then our meromorphic tensor product comes from conjugating that coproduct by this R minus morphism. So we define a new coproduct by conjugating by R minus. Here we actually do have to use this universal formula for this to make sense. So it uses the universal version. And then we've sort of reconstructed everything backwards, but this has all of the structures that we want. We have a category with a tensor product, a meromorphic tensor product, and an intertwiner between these two. So now let's ask what we're going to expect from the Orientifold version of this construction. So first we're going to do the example of Fordich and Simons, and then kind of reconstruct some expectations by what happens in that case. So the Wilson line operators at an Orientifold singularity in Fordich and Simons were studied in this paper by Biddleson and Skinner. And here the data that they need is a Zima-2Z action on the gauge group. This defines a symmetric pair, namely a Lie algebra, and then a subspace consisting of the fixed points of that underlying Lie algebra. So that G gets decomposed into the plus one and minus one eigenspaces of that group action. Then if we take Z2Z that acts on the current algebra by sending like X in G gets sent to sigma of X and U gets sent to minus U, then we get a universal enveloping algebra of that fixed point Lie algebra. And this gets quantized to an algebra called the twisted Yangian, which is a filtered deformation of that enveloping algebra, which is no longer quite a Hopf algebra. So it's still a subalgebra of the Yangian, but now it's quantized into a co-ideal subalgebra. So instead of a coproduct, we get a coaction. So from the twisted Yangian, we get a map to the tensor product of the Yangian and the twisted Yangian. And analogously to the Yangian's construction using R matrices, the twisted Yangian has a description in terms of K matrices. So given some collection of representations and a collection of R matrices that satisfies the Yang-Baxter equation, the group action also defines an anti-automorphism of the corresponding algebra, and we want our representations to be closed under this automorphism. So when we pull back along the automorphism, we want to get another module in this category. The twisted Yangian can be defined by, again, a collection of modules for that algebra, and then a collection of K matrices, where our K matrices, these live in, just like the R matrix, there's two different ways of thinking about them. You can think about them as an endomorphism of a particular thing or of a braiding conjugated by the outer automorphism, but here we're going to think of it as living in endomorphisms of some V tensor M, and again, we're going to take power series in Z inverse, which is an expansion of meromorphic elements. And these K matrices are required to satisfy a compatibility identity with the R matrix. So these should satisfy the braid relations relations for type C braid groups, type B or C braid groups. Or in other words, we've kind of replaced the braid relations for the type A2 root system, saying that these two ways of going around this diagram of roots agree with each other, with the corresponding braid relations for the type B2 or C2 root systems, which say that as we go along these chains of four reflections, we get the same thing.
When you have a braid group type B or C appearing, so you have order 2 action. So the order 2 action on the Lie algebra, assume this time your Lie algebra is type A. It's the diagram automorphism of the Lie algebra. Am I right?
So, in our examples, we can get a diagram automorphism. Usually the examples that are going to be considered compose the diagram automorphism with the Chevalier involution on the underlying algebra. But there's actually a tremendous amount of flexibility in this story. So you can
you don't have this order 2 group acting on the algebras, and also order 2 if you can pull down a little bit, and order 2 group acting on this parameter u. Am I right?
Yeah, that's right.
Okay, so it's just acting on the u by sign plus or minus 1.
Exactly. Yeah,
okay.
Plus or minus
yeah,
1 on the u variable, and then also on the algebra simultaneously.
Thank you.
So we get this braid group action, and the first sort of lemma or proposition you want to notice is that that's the finite dimensional Yangian modules act on this category of twisted Yangian modules. So given a K matrix, so a compatibility of your particular module with all finite dimensional Yangian modules, then we can define a new K matrix coming from the R matrices of the underlying category of finite dimensional Yangian modules and the K matrices that we started. So how do we do this? Well, we just want to find a way to sort of braid our given strand along the juxtaposition of two other strands. And we just compose the braiding in the category of Yangian modules with the underlying K matrix that we start with. So in this way, we actually get kind of a categorical action. We get an action of the category of lines on the category of Orientifold lines. So let's try to take what happens for Orientifold lines in Fordich and Simons and cook up expectation for what happens in general. So what's our data? When we want to have a category of Orientifold lines, this is going to be determined by this group sigma, which in particular is supposed to send the category of ordinary lines to its opposite category, and this is opposite with respect to both monoidal structures because of how the involution is supposed to act on the directions in our field theory, so it inverts both the extra topological direction and the vertex direction. We also expect monoidal module structure for this category. So just like finite dimensional Yangian modules act on finite dimensional twisted Yangian modules, we should have a corresponding structure for lines in this category. And then we also expect a chiral version of the chiral tensor products. So we want a family of module actions that depend on a particular Z that act meromorphically, together with a reflection version of this braiding, which in our case is going to be an identification, a meromorphic identification between L box tensor M with the reflected box tensor of the same element. And we also expect the same type of compatibility morphism between when we choose to fuse our objects in the topological direction and then when we choose to fuse them in the holomorphic direction. So this is a morphism exactly of the same type as in the R matrix case. And then here we can actually sort of see what the compatibility is that we want. So the R matrix compatibility is exactly the same. But what does this compatibility say? It says that if we use this twist in two different orders, we get the same diagram. So our first choice of twist is we've translated our first line by Z, translated our second line by Z plus W. Then twisting on the second factor, we should get, twisting in the first factor, we should say that this is the same thing as L and then the meromorphic tensor product with this other box tensor. And then twisting on the second factor should identify this with L, twisting on the then the meromorphic tensor product in the first and second factor, and the meromorphic module structure on the second and third factor, that should be the same as if we do it in the other order. If we notice that this is the same as the translation of this tensor product, and then the module structure on M, then here we use the K compatibility followed by, there should still be a L prime, followed by the associativity of the vertex tensor structure. And then the theorem / work in progress is that in quite significant generality, we actually get all of these structures. So the real work in progress result that was this paper that we're currently writing with Wenjin says that given CY3 abelian category A, together with an anti-involution on that category, and then we need some mild assumptions in order for the construction to work. So we need the existence of a CoHA, which is like recently been proven by now I'm gonna butcher the long list of authors, but Satsuki Kinjo and collaborators, a cohomological Hall algebra, so a certain associative algebra that you can construct from the data of this category. And then one other sort of main assumption that we need in order for this twisting construction to work is the finiteness of Jordan-Boulder filtration. So we need to be able to define a vertex version of an antipode on this associative algebra together with the vertex Hoff structure. But regardless, say with some relatively minor constructions, we can construct such a braided category together with a monoidal structure and compatibility twist between the monoidal and chiral monoidal structures. Then our conjecture is that with the same automorphism, we can construct a module category together with the braiding module structure, chiral module structure, and compatibility map that satisfies all of the above listed axioms. So maybe I'll briefly mention the strategy and some amount of a plan for what we're going to discuss in the next couple of lectures. So the first thing we need to start with is the cohomological Hall algebra itself. So from the abelian category, we want to construct an associative algebra A. Physically, this is meant to, coming from ideas of Davide Gaioro, Whaley, and Nikita Grigoriev, this algebra is supposed to correspond to a certain three-dimensional object in this 4D theory. So the algebra A is an algebra of operators that lie of an interface between an abelian or like trivial theory, close to trivial theory, on one side of the interface, and then the actual theory that we care about over here on the other side of the interface. And this is extremely similar to what Tudor explained a couple of weeks ago in the 3D context. Then what sort of structures do we get on this category? Well, these are mainly encoded in these vertex by algebra axioms, which gives us the chiral half of this corresponding category. So everything that lives on this interface doesn't see this topological direction, so we only get chiral tensor product and also a braiding. We can't see the standard tensor product or minus. Also on this interface, what we're going to do, and this is the work which was done with Latintsev last year, is we define a category of lines that actually live on this interface. So if we take the interface, which is fixed by this Z mod 2Z action, or intersects the origin, then we get a category of lines which are at the Orientifold point coming from lines in the 4D theory on this RG interface. And this is the physical motivation comes from Orientifold lines living on the interface, but we define this purely mathematically in terms of data coming from the cohomological Hall algebra. And then the last step, which is the most involved, is to, for these types of lines that live on the interface, what additional data do we need in order to, one, let them move into the bulk UV theory, and then two, construct the identification between the two tensor products. First for the just the category of lines itself, and then also for the category of lines that lie at the Orientifold. So the construction that we have is a version of the Drinfeld center. So in 3D, 3D, starting from line operators that live on some interface between a trivial theory and the bulk 3D theory, these are lines on the interface is this category C or G. We can construct the category of lines in the bulk as the Drinfeld center of this category. So we define the category of lines in the bulk, or our model for the category of lines in the bulk, as the Drinfeld center of that category. And in our setup in 4D, we start from this chiral category CRG, which is modules for a vertex by algebra. So this is modules for A. A is a vertex by algebra. We construct an additional category, which we call the chiral center of CRG. And then we show under the given assumptions that there exists a tensor product and meromorphic twist, giving the rest of the data needed to find this category. C tensor Z, beta of Z and R minus. And then the conjecture is that you can do all of the same constructions in this Orientifold case and get a module category for that. So this is roughly the plan for the next 2 lectures, is to explain the steps in this project in order to get this construction.
All right. Okay. Thank you. And Sam, I ask you to send me updated notes. Yeah, because you make few remarks.
Sure.
Yeah. All right. And okay, so then we'll see you tomorrow at the same time. Yeah.
Or it was Wednesday, no?
Yeah, correct. Today is Monday, Wednesday. Yep, you're absolutely right. On Wednesday. Yeah. Okay. Sorry. Okay. This is it for today. Thank you.
Thanks so much.